In chapter 2, we shall learn about the algebra of tensors. Actually, to develop any subject, we need some algebraical operations to be defined. So, in algebra of tensors, we shall learn addition and subtraction of tensors, scalar multiplication of tensors, equal tensors, contraction of tensors, and outer multiplication or outer product of tensors. So, this we will learn in our following module, module 1 of chapter 2. So, in chapter 2, module number 1, we shall learn firstly the addition and subtraction of tensors, scalar multiplication of tensors, that means a tensors will be multiplied by a scalar and what will be its form, equal tensors, what are the equal tensors, contraction of tensors, which is very important for the tensor algebra, and outer product or outer multiplication of tensors. With the help of contraction of tensors and outer product or outer multiplication, we also define inner product or inner multiplication in this module. Now, addition and subtraction of tensors. If ai1, i2, ip and j1, j2, jq and bi1, i2, ip and j1, j2, jq are components of two tensors of type pq, then addition or subtraction of the components will also form another tensors of type pq. So, for addition and subtraction of tensors, the tensors should be of same type, that is important, that the tensors should be of same type. Here it is given in the type pq form. So, after addition or subtraction, it will be of same type of tensor pq. Now, the scalar multiplication of tensors, if phi is a scalar function and if it is multiplied with the components of the tensor of type pq, that a i1, i2, ip to j1, j2, gq, then again it is a tensor of type pq. Now, equal tensors, if a i1, i2, ip and j1, j2, jq and b i1, i2, ip and j1, j2, jq are components of two tensors of type pq in the same coordinate system, then they are said to be equal if they are component wise equal. That means, a i1, i2, ip, j1, j2, jq is equal to b i1, i2, ip, j1, j2, jq. So, in the first three definitions, we just see that how the addition and subtraction of tensors are done and how the multiplication with a scalar can be done and what is the definition of equal tensors. So, in this section of chapter 2, we learn about contraction of tensors, which is very important part of tensor algebra. In our vector algebra, we have learned the resolution of vectors and studied about the components of the vector in various fields. Here, the contraction of tensors also give the components which are very useful in various sections. So, let us see how the contraction of tensors is defined. if A I1 I2 IP and J1 J2 JQ are the components of tensor PQ, where P not equal to 0 and Q not equal to 0, then the quantities obtained by replacing any upper index IT and any lower index JL by the same index IT and summing over it, that means summing over that IT, we get a new tensor of type P minus 1, Q minus 1, that is one less from the contravariant index and one less from the covariant index. This operation is called contraction. For example, let us take a tensor of type 2, 3, that is a mixed tensor of type 2, 3, where the contravariant index are ij here and covariant index a KLM. Then we have, by the transformation law of the tensor of type 2, 3, we have this one, A bar ij KLM equals to del x bar I, del x p, del x bar j, del x q. These are for the contravariant part, and del x r, del x bar k, del x s, del x bar l, del x t, del x bar m, that is they are the for the covariant part with A p q r s t. This is the transformation rule for mixed tensor of type 2, 3. Now we make the contraction. Replacing the lower index L by the upper index I. So we are contracting I and L, and taking summation over I, we get A bar ij k I m, because we have written I equals to L. So in the right hand side expression also we change L to I, that is del x bar I, del x p, del x bar s, del x bar I, del x bar j, del x q, del x r, del x bar k, del x t, del x bar m, A p q r s t, which takes the form this one. So they are the new components B r j k m equals to del s p. From the first two factors of the previous expression, we get del x s p, and then the last part del x bar j, del x q, del x r, del x bar k, del x t, del x bar m, A p q r s t. So which takes the form, if we take S equal to P, B bar I j k I m equals to this one, del x bar j, del x q, del x r, del x bar k, del x t, del x bar m, B q r t. Where A p q r p t is denoted by B q r t. So this one B j k m is a tensor of type 1, 2. At the beginning, the tensor was of type 2, 3. So after contraction I and L and summing, we get tensor whose components are B, J, K, M type, which is a tensor of type 1, 2, and B, J, K, M is called contracted tensor and the operation is called contraction. Let us take another example. Suppose A I j k is a tensor of type 2, 1 in a two-dimensional vector space. That means A I j k are the elements of V tensor product V tensor product V star. and V is a dimension of 2, V has dimension 2. So, Aijk has 2 cube, that means 8 elements or 8 components. Aijk has 8 components. So, the 8 components are, these are the 8 components A111, A121, A211, A221, A112, A122, A212 and A222, because ijk are running from 1 and 2, because we have taken the dimension of the vector space as 2. Now, if I take the contraction, by contracting j and k and summing, we get, so we are taking j and k equal, so we get 2 components A111 plus A121, that we denote by B1, and A211 plus A222, and that we denote by B2. And here we can make another contraction, that is I equal to k. We can take I equal to k and summing, we get A111 plus A212 equals to C1 and A221 plus A222, that we denote by C2. So, from Aijk we can have different components. One, when we contract j and k, we are getting the components B1 and B2, and when we are contracting I and k, we are getting the components C1 and C2. Next, we define the outer product or outer multiplication. So, this is a multiplication of the components of tensor, that if ai1, i2, ip and j1, j2, jq and b, k1, k2, kr and t1, t2, ts are the components of two tensors of order or of type pq and rs respectively, then outer multiplication of these components will give rise to a tensor of type p plus r and q plus s. This operation is called the outer multiplication. For example, torque, we can consider torque as the outer product of the force vector and the displacement vector Fi and dxj, and which is a tensor, we can consider it as a tensor of type 1, 1. Area, if I denote it as dxi and dxj, then it is a tensor of type 2, 0. So, the outer multiplication means the component is written side by side and the tensor will be of type the sum of their components. In previous two sections, we have learned about the contraction of tensors and outer multiplication of tensors. With the help of these two operations, we can define another product or another multiplication called as inner product or inner multiplication. This is actually the generalization of the dot product of the vectors. So, in the next few slides, we shall define inner product or inner multiplication with some examples. So, in this section, we define the inner product or inner multiplication of tensors. In this section, we define inner product or inner multiplication. If an outer product of two tensors is contracted with respect to an upper index of one factor and a lower index of the other factor, then the tensor obtained is called an inner product or inner multiplication of two tensors. So, first we do the outer product of two tensors and then we contract upper index of one factor with lower index of the other factor. So, here we can give an example of inner product or inner multiplication of tensors. So, this work done, which is fi dxi, this is a scalar quantity and this is the example of the inner multiplication of force vector and the displacement vector. The outer product of force vector and displacement vector gives the torque, but if we do the contraction of that two factors, then we get the work done, which is a scalar quantity. This is a result. We can prove this one, that inner product of two tensors of type, one is PQ and another one is BIJL, is a tensor of type 2 1. After inner product of the components of these two tensors, APQ and BIJL is a tensor of type 2 1. Let us see that how it is following. Since APQ and BIJL are tensors, rather components of tensors, so they follow the transformation rule of tensor quantities. That means A bar PQ equals to del x bar P del x n del x n del x bar Q A m n. This is the transformation rule for APQ, and B bar I j l can be written as del x bar I del x k del x bar j del x t del x r del x bar l b k t r. So, this is the transformation rule for a 2 1 tensor. Then for the outer multiplication of these two tensors, we have this form A bar P Q B bar I j l can be written in this form, by writing the side by side, the right hand side, del x bar P del x m del x r del x bar l del x n del x bar q del x bar I del x k del x bar j del x t A m n and b k t r. Now, we make the contraction by taking p equals to L and summing over p, we get this factor A bar P q B bar I j p. We have taken L equals to p. So, this gives rise to this factor in the right hand side, that del R m with del x n del x bar q del x bar I del x k del x bar j del x t A m n b k t and r. So, summing we get this form A bar P q B bar I j p del x n del x bar q del x bar I del x k del x bar j del x t A r n b k t r. So, when we take the operation of Christoffel symbol, this m will be replaced by r. Now, writing A bar P q B bar I j p equals to C bar I j q and A r n b k t r equals to C k t n, we get this form C bar I j q equals to del x n del x bar q del x bar I del x k del x bar j del x t C k t n, which is the transformation rule for tensor of type 2 1. So, the inner product of the tensors of components with APQ and BIJL is a tensor of type 2, 1. The outer product of AI and BJ of the vector AI, and that is a contravariant vector AI and a covariant vector BJ, when contracted for their indices I and j, produces a tensor of type 0, 0, which is a scalar, and that is why the work done is a scalar quantity. We can easily see this one, that it is a scalar quantity. This inner product is called the scalar product of the vector AI and BJ, which is the generalization of the dot product of vectors. So, in module 1 of chapter 2, we have learned the operations of tensors like addition and subtraction, the scalar multiplication of tensors, contraction of tensors, which are very important part of this tensor algebra, and outer multiplication of tensor, that is just the generalization of the vector product of tensors, and the inner multiplication of tensors, that is the generalization of the dot product of tensors, has been done with some examples and with a result. With this, we end this module 1 of chapter 2.